Good afternoon, everyone, and welcome to the second in the series of the AFWI seminars. My name's Mark Brown. I'm the director of the AFWI Centre for Sustainable Futures, hosted at the University of the Sunshine Coast. And I'll be doing introductions today and then passing the microphone to our feature speaker. I'd like to start by acknowledging the traditional custodians of the land. We're joining you from Cubby Cubby country in southeast Queensland, and pay our respect to their elders past, present and emerging, and I extend that recognition to all lands where people are joining us today online. I'm quite excited to introduce, and in many cases reintroduce, Mauricio to the Australian forest sector. So Mauricio has been appointed as the AFWI industry chair for system-based thinking and AI integration for forest productivity. So he's been provided a position to work with industry over the next 4 to 5 years on how best and how to effectively use the emerging tool of AI for industry innovation and productivity, cost reductions, and all of those good things. So this afternoon, Mauricio is going to give us a brief overview of some of the plans he's putting together with his industry steering committee and give us a bit of insight into some of the research opportunities, and the conclusion will be available for questions. So with that, and screen sharing's working well, so that's a positive. I'll pass the microphone to Mauricio.
Yeah, okay. Thanks a lot, Mark. Can you hear me well?
Yes.
Excellent. Perfect. I'm going to move it to share that, and we can start with move the windows. Okay. Yeah. Hello. Thanks, Mark, for the introduction, and also thanks to all the people who are connected today. So today I want to share my vision for this industry chair and the industry problem is designed to address. The central idea is simple. Producing more timber is not only about growing more trees, it also depends on how we shape the resource, move it through operations, and convert it into products and value. For example, increasing harvest volume creates little additional value for transport, mill intake, or product recovery is the real constraint.
He might be at his desk.
I'll not be coming in. I'll come in for a while. Yeah.
I thought you were. Yeah.
Oh, right. Okay. AI sensing and optimization are therefore not the final objective of this chair. They are just tools for making better, explainable, and coordinated decisions across the forest value chain. My goal today is to show how system thinking, decision intelligence, and forest AI, the platform that I am proposing for this chair, can connect those decisions and where industry can help us test them. My background combines forestry, operations research, and technology. I began with forest engineering at the University of Chile, followed by a master in operations management at the University of Chile, with a strong focus on forest harvesting optimization. 20 years ago, I completed my PhD at Oregon State University, and my research connected internal wood properties, sensing, optimal packing, and value recovery. For more than 30 years, I had worked across research, teaching, and industry. So for 7 years, I worked for a private company in Chile. And 3 years ago, I moved to Finland, where I work as a research professor in forest technology. So that experience had led me to 4 complementary capabilities. System dynamics helps me understand how the whole system behaves. Sensing tells us what is actually happening. Optimization helps us choose the best feasible action. And AI helps us predict, recognize patterns, and learn from experience. So I don't see this as 4 separate technology programs. Their value comes from connecting them around a real decision. For example, which trees to remove during thinning, or how harvesting and mill intake decisions should be coordinated. As you can read at the bottom, technology matters when it improves a real decision. Yeah, as I said before, I worked for 3 years in Finland. I just came back to Australia a couple of months ago. And among others, my work in Finland reinforced a simple lesson. Sensing is valuable only when it changes the decision. So in Finland, we connected UAV LiDAR, ground-based LiDAR, vision systems, harvester data, and optimization. So the pathway did not stop at measurement. Evidence characterized the trees, optimization supported the prescriptions, machine records showed what was executed, and actual outcomes improved the next decision. That is the connection I want to bring to Australia. Measurement, prescription, execution, and learning as one practical loop. So this is the journey I will follow today. I'm going to begin with why connected decision mattered for Australia's timber challenge. I will then introduce Forest AI as the environment that connects evidence, models, and explainable choices. The third part brings together two complementary PhDs, one at a tree and stand level, the other across the whole value chain. And I will finish with how industry cases, governance, and decision intelligence lab can turn individual projects into an enduring capability. Australia is not facing one uniform shortage of every timber product, but it does have a substantial forest and wood product trade deficit. In 2024-2025, imports were 6.83 billion and exports were around 2.89 billion. So a gap of approximately $3.94 billion. At the same time, ABARES indicate that structural softwood demand may rise by up to 50% by 2050 as population and construction needs grow. Reduced native forest harvesting in Victoria and Western Australia is one contributor, alongside plantation availability, processing capacity, and the mix of product that domestic sector can supply. This chair cannot solve this through one algorithm or simply by waiting for new plantations to mature. My focus is to help industry obtain more timber and value from Australia's available resources through better thinning, better silviculture, sensing, optimization, recovery, and coordinated decisions across the value chain. I see timber production as the result of three connected conditions: how we shape the resource, how reliable it flows, and how effectively it's converted into products and value. Silviculture and thinning determine the quantity, timing, and quality of future merchantable timber. Harvesting, transport, workforce, and infrastructure determine where that timber reaches the right place at the right time. Processing, specifications, and markets determines how much usable product and value will finally recover. So a weakness in any one of these conditions limits the whole system. So an excellent thinning regime may create high quality future timber, but its value will not be realized if harvesting capacity, transport coordination, or mill recovery becomes the defining constraint. This is why the chair cannot be reduced to one algorithm or sensing project. The opportunity is to improve the connected decision system. So this program brings together four capabilities, as you can see here on the left, but they serve one integration goal. System dynamics help us understand stocks, flows, feedback, delays, and leverage points across the value chain. Sensing provides evidence about the actual conditions of trees, machines, and operations. Optimization identifies the best feasible action under real objectives and constraints. AI helps us recognize patterns, prediction outcomes, adapt, and explain recommendations. So the order here matters. If we don't understand the system, we may optimize the wrong intervention. If we do not observe the real condition of the operation, a mathematically precise model may still be wrong. If we only predict what will happen, but we don't optimize the decision, we have information without action. So Forest AI, the platform that I'm proposing for this program, brings these capabilities together through a continuous cycle. Observe the system, understand its behavior, choose an intervention, and learn from the outcome. So the value chain already behaves as one connected system, even when its organization, data sets, and decisions remain separate. This section explains why local improvements can fail to improve the final industry outcome and why capacity, information, feedback, and time must be considered together. So this is the basic decision system, from the standing reserve through silviculture, harvesting, transport, and processing. Every stage changes what becomes possible downstream. Thinning, for example, affects future tree size and quality. Tree selection and bagging affect the products available for transport. Delivery timing affects mill inventories and production schedule. But the information must also move upstream. If a mill expects stronger demand for a particular product, that requirement should influence bagging, harvesting priorities, and over longer horizons, silvicultural choices. Integrated decision intelligence connects decisions in both directions. Downstream requirements shape upstream objectives, while actual operational and processing outcomes return as evidence. Without that feedback, every stage may perform well against its own KPIs, while the complete value chain performs poorly. So a decision that appears optimal locally can create a new bottleneck elsewhere. For example, maximizing the harvesting production can lead more volume at the roadside than the available trucks can move. Minimizing transport costs can produce an efficient route plan that delivers the wrong product mix or misses an important intake window. A mill can improve internal recovery, but it cannot recover value from unsuitable logs or unstable supply. So the important question here is therefore not whether each operation is individually efficient, it's whether the coordinated set of decisions improve total production, recovery, resilience, and value. So this changes the unit of optimization. If the objective is whole chain performance, the model must recognize interactions across contractors, fleets, facilities, and time. Otherwise, the optimization may simply transfer the constraints. Integrated decisions may require decision-making requires more than sharing data. Decisions made over different time horizons must influence one another. At the center is a shared system state, the reserves, machines, queues, demand, and uncertainty. Evidence from LiDAR vision system stand for the machine records, telemetry, and mill outturn updates that state. So operational decisions occur over minutes, hours, or days, for example, tree selection, bagging, and dispatch. Practical decisions cover weeks, months, or even years, and that includes harvest areas, fleet plans, and mill intake. And then we have strategic decisions, which extend over years, and that are related to silviculture, infrastructure, capacity, and investment. So the critical point is that actual outcomes must return to the shared state and change the next decision. We compare intent with outcome, production achieved, waiting time, recovery, or product value. If conditions or assumptions have changed, the recommended action should change as well. Otherwise, we are collecting data and producing reports, but not building a decision system that can learn. So here I would like to introduce the concept of system dynamics. System dynamics gives us 4 practical building blocks. Stocks are things that accumulate. For example, in forestry would be standing volume, age classes, roadside inventory, log yards, queues, and processing capacity. Flows increase or reduce those stocks. For example, growth, thinning, harvesting, transport, processing, and demand. Feedback occurs when the state of the system changes future decisions. For example, a full mill yard may slow deliveries. Low recovery may change future bagging instructions. A persistent timber storage shortage may trigger investment. Delays separate an action from its result. For example, thinning influences stand development over years, while new infrastructure may take years to plan and construct. So a system dynamics model combines these elements quantitatively. It's not merely a flow chart or another forecast. It helps us understand why behavior emerged and test interventions before committing resources. And here we have a practical example that makes feedback concrete. Suppose deliveries to a mill are below target, so more trucks are assigned, as you can see on the left. More trucks increase the arrival time, but if mill intake capacity is unchanged, the queue becomes longer. And longer queues increase turnaround time. So each truck completes fewer trips, effective delivery capacity falls, and management may respond by assigning still more trucks. The plus or minus signs describe the direction of influence. For example, at the beginning, more trucks will, turn into a higher arrival rate at the mill. So together they form a reinforcing capacity trap. This doesn't mean that an additional truck is never useful. It means that decision must be tested within the wider system. The leverage point may be coordinated arrival times, shared forecast, intake windows, or product sequencing. So once the intervention is identified, detailed transport optimization can determine the best schedule. Not every intervention has the same leverage. At the simplest level, we can adjust parameters, for example, track numbers, shift length, buffer size, or thinning intensity. Those changes may help, but the effect can remain limited when the system structure is unchanged. So greater leverage can come from information and decision rules. Earlier access to mill demand forecasts, for example, may improve coordination without adding physical capacity. Deeper intervention may change responsibilities, capacity, or investment timing. And then at the deepest level are goals and mental models. If every participant is rewarded only for maximizing local utilization and performance, the whole chain may remain inefficient, even when each local optimizer performs perfectly. This is why system dynamics and AI optimization are complementary. System dynamics help us choose the right intervention. Optimization AI help us implement that intervention effectively. I see Forest AI, this platform, as a scenario laboratory for the whole value chain. On the left are decisions that we can change. For example, thinning strategy, harvesting and transport capacity, and mill demand or product mix. We work with industry to map the important resources, decisions, capacities, constraints, and delays. And then we formalize the critical assumptions in a system model and calibrate it using the best available evidence. These choices enter one connected system model, as you can see in the middle here. We can then explore plausible futures, changes in thinning strategy, constrained harvesting capacity, a different mill products mix, or delayed processing investment. The purpose is not one perfect long-term forecast, is to understand consequences, sensitivities, and trade-offs, and identify interventions that remain valuable across several plausible futures. We can then compare a baseline future, a targeted intervention, and in an unintended consequences case. For example, adding transport capacity may improve timber flow or simply move the queue to mill intake. The comparison shows where benefits appear, how long they take, and what trade-offs emerge in production, utilization, recovery, and value and risk. So detailed AI and optimization tools then help implement the selected intervention. So the response from this chair is Forest AI, the platform, and two complementary PhD projects. These projects operate at different scientific scales, while Forest AI reconnects their evidence, models, scenarios, and explanations. It is a research and innovation platform, not a replacement for partner operational system. And here I have to clarify well this, because I'm not competing with any commercial platform or system that the industry is already using. For now, it's as a research and innovation platform. Forest AI should be understood as an integration environment, not another operating system that industry must adopt. We begin with existing industry systems, sensors, operational records, planning tools, and expert knowledge. A governed data fabric connects relevant evidence while preserving identities, assumptions, and provenance. That evidence supports useful representation of trees, stand machine fleets, mills, and value chains. That's the digital representation. We then apply the method appropriate to the decision. For example, system dynamics, simulation, optimization, or AI. Alternatives can be tested and compared, uncertainty exposed, and the reason for the recommendation explained. For example, Forest AI could connect a thinning prescription with actual harvester records and later stand measurements. It could show why the prescription was recommended, what happened during the execution, and what should change next time. So that continuous connection between research evidence and operational experience is Forest AI's distinctive role. This interface is deliberately illustrated. It's not the definite Forest AI design or commitment to build every module exactly as shown. In fact, I don't know if I'm going to maintain this name Forest AI because I did a search online and there's already some organization using that name. So it could also have a different name in the future. The purpose of the platform is to make, its purpose is to make the platform tangible. We can imagine reusable services for transport, harvesting, bagging, traceability, and carbon, and even more in the future. So a shared view can expose scenarios, constraints, schedules, and performance. An assistant can help user ask why an outcome occur and what happens under a different assumption. For example, instead of merely showing that a truck is waiting, the system could help a manager determine whether the cause is product availability, the delivery window, meal intake, or another constraint. The important idea is not the screen itself, it's the integration beneath it. Interoperable evidence, scenario comparison, traceable recommendations, explanations, and human review. The eventual interface must be co-designed around real industry decisions. That's the important thing. Bring the decision intelligence cycle and the permanent lab capability together. Using, again, thinning as an example, we first integrate LiDAR, vision systems, inventory, and operational expertise into a shared decision state. We model tree competition, growth, quality, and value. We then test alternatives, whether to thin, when, the intensity, and which trees to retain or remove. The recommendation must be explainable. So a forester, for example, should be able to see the evidence, the assumptions, alternatives, expected consequences, and uncertainty before acting. After implementation, the removed trees, machine records, residual stand, and later growth return as evidence. If actual outcomes differ from the prediction, the model and the next recommendation must change. Forest AI connects the evidence and analytical services. The decision intelligence lab makes this a repeatable industry research practice, preserving the decision record, comparing intent with outcome, and turning each case into better rules for the next decision. When I talk about AI, I don't mean removing people from decisions. Human-centered AI is designed around the forester, the planner, operator, or manager, who remains responsible for the choice. Explainable AI should show the evidence used, the alternatives considered, the expected consequences, and the uncertainty involved. A thinning system should not simply recommend removing a particular tree. It should show how that choice affects residual quality, future growth, and value. The same principle applies across the value chain. A recommendation should reveal whether it's driven by a product requirement, a delivery window, capacity, risk, or another constraint. The responsible person can then accept, modify, or override it, and the human judgment becomes part of the decision record. So that is the meaning of this quotation. A solution creates value only when people can understand it, trust it, and implement it. The next section introduced the 2 PhD projects. And so this chair came with funding for 2 PhD projects. These two PhD projects are complementary rather than competing. PhD A improved decisions that shape the future research, while PhD B improved the system that converts that research into production and value. And Forest AI connected the evidence, the models, and the scenarios between those scales. So here we have a picture of how all these things are integrated. So as I said before, the two PhD address one shared objective are two connected decision scales. PhD A on the left works close to the biological research. It asks how thinning decisions can increase future merchantable timber and value, whether to thin, when, how intensively, and which tools to retain or remove. On the right, PhD B works enterprise and value chain scale. It asks where bottlenecks, feedback, and leverage point constrain production and value across harvesting capacity, transport, processing, workforce, demand, and investment. For example, PhD A may identify a prescription that improves residual growth and future soil log recovery. That value will only be realized if the wider system has the capacity and coordination to convert it into an industry outcome. Forest AI in the middle bridges the scale through shared evidence, models, scenarios, and explanations. One project improves the research, the other improves the system that turns into production and value. PhD A is a thinning decision intelligence project. It's not a sensing project. The pathway begins by characterizing the stand and individual trees using LiDAR, computer vision system, inventory, and machine data. It evaluates growth, quality, and operational feasibility. Optimization then compares prescriptions against merchantable yield, residual stand quality, future growth, product recovery, and value. Consider a light thinning now versus a heavier thinning later. Both may satisfy a basal area target, but they can produce different residual quality, soil log recovery, operating costs, and risk. The recommendation must explain those alternatives and trade-offs, not simply output one number. And finally, the prescription is validated using the trees actually removed, machine records, residual stand condition, and later growth. Forest AI packages the pathway as a reusable service. The scientific endpoint is the thinning decision and its consequences. Sensing, prediction, and optimization are enabled components. PhD B asks where bottlenecks, feedback, and leverage point constrain production and value across the complete forest value chain. So we begin here by mapping stocks, flows, capacities, delays, decisions, and information hands-off across the research, silviculture, harvesting, transport, processing, workforce, demand, and investment. We then translate the important structure into a calibrated causal loop or stock and flow model. These are components of when you are modeling a system dynamics system. So the visible problem is not always the leverage point. For example, trucks waiting at a mill may appear to be a transport capacity problem, while the actual cause could be harvest, release, product mix, shift timing, or intake rules. So the model identifies where detailed analysis is justified. We then use the simplest suitable operational model, optimization, simulation, a digital twin, or AI, to test the intervention. We do not force every tree, truck, and mill into one monolithic model. And the output is whole chain scenario intelligence, where to intervene, why it matters, when benefits appear, and what trade-off industry should expect. And integration is a two-way learning loop, not a one-directional transfer of data. So a strategic requirement flow upstream. You can see the brown arrow at the top. Demand, mill specifications, capacity, workforce, and investment conditions shape the questions tested by PhD B, and the scenarios in Forest AI, and eventually the objectives used by PhD A. Measured outcomes flow back through the system: tree response, harvested volume, operating performance, recovery and value update the share state, and improve the next model and decisions. For example, a stronger demand for structural sawlogs may change thinning timing and which trees are retained. After implementation, actual growth, assortments, and meal recovery are compared with predictions. Those results reshape both the next thinning prescription and the wider value chain scenario. That closed loop is the integration. Stand decisions inform the system model, and industry outcome reshape future stand decisions. So this is a stage five-year delivery program with two delivered gates. In years 1 and 2, we proved the foundations: map priority industry decisions, establish thinning sites and sensing baselines, build the value chain system model, and create only the forest AI capabilities required for the first demonstrators. Gate 1 asks whether we have demonstrated credible industry value. And then in years 3 and 4, we scale only what has earned the right to scale. PhD-A moves into optimization, field trials, and human validation. PhD-B compares scenarios and case and develops operational submodels where leverage has been identified. Gate 2 asks whether the value has been demonstrated beyond one case. And then we have in year 5, and we focus on transfer. Thesis, reusable assets, strategic scenarios, consolidated evidence, and an agreed pathway beyond this chair. Forest AI and the lab are not 5-year websites. The integration capability grows throughout this program. Yep. So in principle, this is my contract is for 5 years, so this chair will run for 5 years. And here I want to mention something in which I was involved in Europe in the last 3 years. So while in Europe, while in Finland, I was the coordinator of a CBAU project. This is a Horizon project. As you can see here on the left, you have some figures. So it's a 5 million euro project that involves 17 organizations. And so we had also 4 regional cases in Austria, Finland, Spain, and Sweden. So apart from being the coordinator of this project, I was also leading the 4 regional cases. This project is similar to what we are intent to do in this chair, not exactly the same, but it has some common elements. In Europe, we were developing early warning indicator. This is for biotic and abiotic risks, like snow, pests, wind, etc. Adaptive management. So there's a whole work package working on different alternatives for adaptive management and in order to produce more resilient forests. And then there was an operational sort of work package, more focused on sensing and AI. And yeah, to produce more agile operations. And then we combine everything into combined value and LCA, so life cycle analysis. That includes basically everything related to environment and the social aspects of different value chains. And I mention here because we have an opportunity in Australia. And the opportunity is now, as you can possibly read in the media, Australia and the European Commission concluded Horizon Europe Association negotiations on the 9th of June this year. And subject to the treaty process, transitional arrangements are intended to allow Australian entities to access Pillar 2 funding and lead consortia from January 2027. So any organization, research organization, university, or even the industry could eventually participate in those partnerships with European organizations and get funding from Europe. So we should prepare now by identifying relevant goals, strengthening European partnerships, and positioning Australia plantations, native forests, and value chains as high-value demonstration environments. The objective is not to copy Europe, it's to bring Australian challenges and capabilities to larger research and innovation network. And this is going to be one critical and important role for me also in Australia. As the coordinator of this European project, I am familiar with the application process and all the administration rules and things involved in this project. So yeah, my role is going to be also a facilitator for Australian organization to participate in these European projects. And also I have to mention that I'm not alone on this journey. The steering committee brings perspective. So I have established my steering committee, and that brings perspective that no model can supply on its own. So the knowledge of growers, harvesting, processing, logistics, technology, investment, and the realities of adoption. So I need this committee to guide strategic direction, test assumptions against sector reality, connect the program with size, data, and people, and steward the pathway from a promising prototype to a capability industry can use. So the committee should not simply receive reports. It should challenge the research, help identify the decisions that matter, and maintain the balance between scientific quality, industry relevant, and sector-wide benefits. Integrated decision requires integrated leadership. And here you can see all the people that are in my steering committee. So we have Duncan from Forest Corporation as well, Jan from 141, Ian Hancock Queensland Plantation, Nathan from Sustainable Timber Tasmania, John from the Forest Product Commission, David from High Timber, Mike Saron, which now a consultant but used to work for Forest Corporation as well. And also we had one AI representative, Jonathan Chang from Silver Pond. That's an AI company. And I want to finish just with the last 3 slides. And so the final section moved from research project into an enduring industry capability. Industry cases, co-design, governance, and validation are what make the work credible and useful. The aim is not a collection of one-off demonstration, but a decision intelligence lab that preserves evidence, learns from outcomes, and improves future decisions across the forest value chain. Industry participation does not begin with a request for every data set a company holds. A credible bounded case is enough to start. First, we need a real decision context, perhaps one thinning site or a defined forest to processor case. Second, we need people who understand the operation. That alone cannot explain why a forester changed a prescription, why a contractor delayed an activity, or why a mill rejected a product. And third, access must be governed. The partner remains in control. Purpose, users, boundaries, outputs, and retention are agreed, and information is not reused without any permission. So all the organization, the forest companies, remains the owners of the data. And finally, we co-design the work and agree how value will be measured. For thinning, for example, that could include residual quality, future soil yield, recovery, cost, and operational practicality. So the principle here is simple. We start with a minimum viable case, demonstrate value safely, and expand only when the evidence justifies it. So how I will judge the impact of this chair? I will judge the chair by what the industry can continue to use, not by the number of reports, algorithms, or dashboards produced. Success has 3 connected dimensions. At tree and stand level, better thinning decisions should improve residual quality, future mentionable yield, and value. At system level, intervention should relieve binding constraint and improve production, recovery, and resilience across the whole chain. The third outcome is enduring industry capability. The program must be co-designed with partners, understand how decisions enhance the work in practice, and leave the reusable evidence, models, explanation, and demonstrator through Forest AI and the Decision Intelligence Lab. All 3 dimensions depend on trust. Recommendations must be explainable, decisions auditable, and solutions practical for the people implementing them. For me, the chair succeeds when integrated, explainable decisions become normal industry practice, and when that capability remains after individual projects and students have finished. And I would like to finish my presentation with a question rather than a list of conclusions. Where in your part of the forest value chain could could a better connected decision create the greatest benefit? It may be a thinner decision, a handout between organizations, a recurring capacity constraint, or an investment choice whose consequences are not yet visible. So those decision sites and bounded cases are where this program becomes real. So I welcome your question and your ideas about what we should test first. I'm happy to take questions, but also would be really happy if someone can make comments or provide any feedback about what I had presented in these 40 minutes. And that's it from my side. Thank you very much.
Thank you, Mauricio. I think we'll start. There's a couple, or at least there's one question and one comment in the chat, if you want to have a look at that.
Yeah.
Mauricio, to start with, particularly from Steve Reed, asking about the mobility or transferability of some of the models and work you're discussing.
Yeah, very good question, Steve. I'm going to start with that question. Yeah, everything has to be portable because I have to maintain the independence of this chair. Everything that we produce, for example, the Forest AI platform, could be connected to another commercial platform in the future. So for example, I'm thinking about Trimble or Renzo, they could host the Forest AI platform, but all the modules have to be portable because I cannot, just work with only one commercial partner. I should be open to other opportunities that, emerge in the future. So yeah, responding to that question, I think we will produce interfaces, APIs that connects our platform or any other, platform that the industry is using. And we have already discussed commercialization path with the steering committee, but for now, the conclusion was that I need to focus more on, showing the value first. And then after the second year, possibly we are going to explore other more commercial, commercial sort of pathways. Okay, and that means there could be the integration with existing commercial software, or who knows, in the future could be Forest AI could be the de facto, tool in Australia.
Thanks, Mauricio. Any other questions? Feel free to add it to the chat, or if you want to raise your hand and unmute and ask your question. Okay.
This one, Joseph.
Oh, thanks, Mauricio. Yeah. Very interesting presentation. My name is Vijay. I'm from DAF. Just a quick question. You might have already covered this, but my question is like, what is the scale you are talking about your model? So the forestry industry is quite diverse across different states, different territories. So a model which you are building, a systems model which you are building for New South Wales, can it be still be validly applied to the forestry system in Western Australia? So how are you going to deal with this variety of systems within the sector? That's one question. Are you also considering, when you say systems, it's a very broad word. Are you considering the social and ecological aspects of the system as well, or is it just the industry systems?
Yeah. Okay. So, yeah, I think you're raising a good point. I'm already working with my steering committee to identify value chains, initial value chain, because I need at least case studies for my PhD student. The general concept is to start with something simple, because it sounds very ambitious, but we are going to start with one value chain, possibly here, regional one in Queensland or South Australia, and but then, yeah, in the future, the idea will be to include more value chains across the country, especially for PhDB, because that student is going to do a mapping of the whole value chain in different regional areas. But the idea is to go step by step, possibly at the beginning, I'm going to focus more on the supply chain component of the value chain. So from thinning, harvesting to processing. So that would be also, I didn't mention, but I already had developed several tools in the past. I had harvesting optimization models already. I have a transportation fast track, my transport scheduling optimization system. I'm working now at the moment on automated dispatching system for transport planning. I had developed backend systems in the past, how to optimize cross-cutting. So we have some modules already developed, but in terms of the value chain, yeah. So we are going to start with 1 or 2. I already talked to my steering committee, so hopefully I can get at least 2 value chain to start, and that would be the starting point. And in the future, that would expand to other value chain, because I don't want to only include, company with a big, data set, a lot of data. It could be a simple, a company with a more simple sort of value chain. Could be a company that is only producing wood chips or pulp logs in the future. Yeah. So the idea is that continue, the growing of the platform, gradually over time, allocating or using more data, collecting more data, and populating the tool with more data, more models. Then after the first 2 PhD students, there will be another 2. Supposedly they would improve the AI model. They continue working, collecting more data, using other, that's the idea. Start from very humble, but then continue growing consistently over time.
Thank you, Mauricio.
Data acquisition strategy. Yeah, good point. Yeah, I've been in conversation with the steering committee how that should be done. But here, at least I need data, from companies. Everything is useful. For example, LiDAR data, inventory data, machine data, and yeah, that could be, by the way, a challenge, because we are aware that some data is very sensitive. We need to do a mapping of whole value chains. Again, very sensitive information. So yeah, we need to agree with the industry what sort of data we are gonna be shared, at what sort of outputs or results from our study that are going to be published or can be published. But hopefully that's not. It shouldn't be an impediment for me to produce scientific results from this research. And the strategy would be to contact companies first to see what data is available. I mean, for example, harvesting data. Is there any records from the machines or from the contractors or from inventory data? Is there any inventory record that I can use for this research? And this is quite critical because, as you can see from my presentation, data is the key input here. Without that data, we cannot develop the optimization model or AI, and this is quite critical. Okay, so it's something I need to discuss with the industry and with the companies that are going to host the studies. And just a last comment about data. Yeah, I think in the near future, I'm going to prepare like a document that basically provide guidelines for data governance. How that is going to exchange, what is the format, etc. What happens if one company decide to move away from this program? What we are going to do with that data. So it can be deleted, could be reused, or what sort of a strategy we are going to have in the future. From Steve again, the different commercial players in non-integrated value chain will respond to their own local incentive. Once the system is understood, how do you set these local incentives so they optimize the whole system, not just transfer a bottleneck? Yeah, that's a good point. Yeah, exactly. Yeah, that's a good point. We need to find ways how to share the, if we are improving the system at a broader level, how everyone is going to receive benefit from improving decisions at that scale. And yeah, it has to be a win-win sort of situation. Everyone in the value chain should receive the benefit for improving, for improving the outcomes at a system level. And that's quite critical because optimizing something or improving the performance at a system level can be in detriment of one of the components of the value chain. So that component, let's say harvesting, should be compensated for any loss of value. So that would be the strategy. But yeah, that also requires that everyone in the value chain can get the benefits. Otherwise, it's going to be quite hard to implement any solution, at a system level. And also we need to identify which links in the system are the critical ones. Could be harvesting and transport, or transport and processing, or yeah, we need to identify those critical links and how those decisions are affecting every stakeholder or every component in that value chain. Very good question. I don't know. I would like to hear if this proposal makes sense, or yeah, it would be good to have a comment on that. It could sound a little bit ambitious, or I don't know, something not really practical, but yeah, it would be good to have a feedback or comment.
Okay, we've just gone past an hour.
Mm-hmm.
Certainly, Mauricio is available and contactable. Email addresses and such. Certainly encourage people to reach out if they have, as he said, comment and feedback about practical application and implications of what he's proposed. So please feel free to reach out to Mauricio, and certainly encourage you to engage with his work, as well as the broader set of research that is being led by AFWI with all of our industry partners. So with that, we might conclude, and thank everyone for joining us, and noting that this is a monthly event, and watch your inboxes for the details of our next presentation.